Welcome to the class of Calculus 1. Cal 1 is a course about derivatives and their applications. As a comparison, Cal 2 and Cal 3 are about integrals and their applications. The textbook for Cal 1 is this book. Actually, this book is also the textbook for Cal 2 and Cal 3. Cal 1 only covers 4 chapters in the book. Chapter 2, Chapter 3, Chapter 4, and Chapter 5. And also covers Section 6.1. About Chapter 2, my teaching schedule is I first teach the second section of the chapter 2.2. I first teach 2.2 first, then 2.1, then 2.3, 2.4, and so on. Today, we study section 2.2. The topic is the limit of a function. Suppose we have a function y is equal to f of x. This function has 2 variables, x and y. The variable x is an independent variable. X can freely assume values. The variable y is a dependent variable. The value of y depends on the value of x. Now, I move the independent variable x toward some point A or some number A. If as x is getting closer and closer to A, dependent variable is closer and closer to some number L. In this case, we say that the number L is the limit of the dependent variable y as x approaches A. Because y is equal to f of x, we also say that the number L is the limit of the function f of x as x approaches A. In notation, we write L is equal to the limit of the dependent variable y as x approaches A, or L is the limit of the function f of x as x approaches A. Here are some conventions about this definition. In the definition, this symbol means closer and closer to approach or tend to. Convention 2. In the process of x approaching A, x is not allowed to take the point A directly. There is no restriction, however, on the dependent variable y. In the process of y approaching L, y can take L. Convention number 3. If as x approaches A, y approaches more than one number. In this case, we say that y has low limit as x approaches A. In other words, this limit doesn't exist, or this limit doesn't exist. This convention requires the limit of y is 1 and only 1. When y, dependent variable, has more than one limit, this case, we say that y has low limit. Limits should be 1 and only 1. Here is one remark about this convention. There are infinitely many ways that x approaches A. For example, we can let x, dependent variable, approach the point A from the left side by first taking this point, then this point, then this point, then this point, and so on. Or we can let X approach the point A from the right side by first taking this point, then this point, this point, this point, this point, this point, and so on. Or we can let X approach A by jumping around the point A. Say we can let X, independent variable, take this point, then take this point, then this point, this point, this point, then this point, and so on. So there are infinitely many ways that X can approach the point A. This convention, number 3, here is a typo. Convention number 3 says that no matter how X approaches A, dependent variable Y should approach the same number. If Y approaches more than one number, we say that Y has no limit. When we study the limit of a function, please keep these 3 conventions in mind. In particular, convention 2, convention 3, keep them in mind. Here are some examples about the limit of a function. Example 1, find the value of this limit. In this limit, the function is x minus 1 over x squared minus 1. And in this limit, independent variable x is approaching 1. When x approaches 1, the function will approach some number. Now the question is, can you tell the number? The number is this limit. Here, the blue curve is the graph of the function. The graph of the function is the set of all the points that satisfy this equation. For example, 0, 1, this point satisfies this equation. When you plug in 0 in x, plug in 1 in y, this equation holds. Also, this point satisfies this equation. When you plug in 0.5 in x, 0.6666, and so on in y, the equation is true. So this point satisfies this equation. Now, all the points that satisfy this equation together, they will form a curve. The curve is the graph of the function, or the graph of this equation. Please note that this function is not defined when x is 1, or not computable when x is 1. When you plug in 1 in x, you will get 0 over 0, not computable. So therefore, I place an open dot here. Open dot means the point is not a part of the graph of the function. At each point of the graph, say at this point, the height of the point is the value of y, or the value of the function. So height of a point on the graph is the function value at the point. Okay, now let me determine this limit. When x approaches 1, I want to see what number the function will approach. I tell the limit by making tables. Yeah, here is one table. The first column is for the independent variable x. Second column is for the numerator. Third column is for the denominator. The last column is for dependent variable y. Y is f of x. Y is the function. Okay. So the last column is for the function. Now I let x approach 1 by taking these points. These points are quite arbitrary chosen. You can choose other points. We call convention number 1. Convention number 2 about the limit of a function. Convention number 2 says that x approaches some point, but x is not allowed to take that point directly. So in these numbers, I didn't pick 1. In the first column, I didn't pick 1 for x. I just net x getting closer and closer to 1. I didn't net x take 1 directly. When x is 0.5, x minus 1 is 0.5 minus 1. It is negative 0.5. X squared minus 1 is 0.5 squared minus 1. It is negative 0.75. The function value, the value of y is numerator over denominator. It is this number. When x is 0.9, x minus 1 is 0.9 minus 1. It is negative 0.1. X squared minus 1 is 0.9 squared minus 1. It is negative 0.19. The function value is negative 0.1 over negative 0.19. It is this number. Similarly, when x is 0.99, function value is this. When x is 0.999, function value is this. When x is 0.9999, function value is this. From the last column, we can see that the value of y is approaching 0.5. So 0.5 is the limit of the function as x approaches 1. So this limit is equal to 0.5. But before we make such a conclusion, recall convention number 3. Convention number 3 says that no matter how x approaches 1, the function should approach the same number. Otherwise, the limit doesn't exist. In this table, I let x approach the number 1 from the left-hand side of the number 1. Here, I plot these numbers on the number 9. Suppose 1, this point is 1. 0.5 is here. It is on the left of the 0.1. 0.9 is this point on the left of the 0.1. 0.99 on the left. 0.9999 is still on the left of the number 1. So in this table, I let x approach 1 from the left side. From the left side. In notation, x approaches 1 from the left. To mean from the left, according to the book, we put a minus sign behind 1. 1 minus means x approaches 1 from the left side. From the left side. So to make sure, when x approaches 1 in other ways, the function still approach 0.5. In the following, I make a second table. In the table, I let x approach 1 from the right side. Here is a second table. In this table, I let x approach 1 by taking these points. If you plot these points on the number 9, then you will see all the points are on the right-hand side of the point 1. 1.5 on the right side, 1.1 on the right side of point 1, 1.01 on the right side. So in this table, I let x approach 1 from the right-hand side. In notation, x approaches 1 from the right side is 1 plus. The plus sign behind 1 means on the right side of 1. The last column of the table also shows that the value of dependent variable y, or the value of the function, still approach the same number, 0.5. So the first table and the second table together, we tend to conclude that the limit of the function as x approaches 1, no matter how x approaches 1, the function approach the same number, 0.5. So the limit is 0.5. Example 2. Find these two limits. The function in the first limit is 5, a constant function. The function value doesn't depend on x. Or you can say that the function depends on x in this way, 5 plus 0 times x. The graph of this constant function is this horizontal line. The graph is the set of all the points that satisfy this equation. All the points that satisfy this equation are the points on this horizontal line. For example, these points satisfy the equation. When you plug in 0 in x, plug in 5 in y, the equation is true. When you plug in 1 in x, plug in 5 in y, the equation is true. So all such points together, they form this horizontal line. The graph of the function in the second limit is this line. The slope is 1. Okay, now to determine the limits, I make tables. For the first limit, I make these two tables. In the first table, I let x approach 2 from the left-hand side. The function at these points are always 5. Therefore, when x approaches 2 from the left, function or dependent variable approaches 5. When x approaches 2 from the right side, dependent variable, the value is always 5. So dependent variable approaches 5. Now, based on these two tables, I tend to conclude that the limit of this constant function as x approaches 2, no matter how x approaches 2, from the left, from the right, the function approaches the same number, 5. So therefore, 5 is the limit. Similarly, to find the second limit, I make two tables. In the first table, I let x approach 2 from the left-hand side by taking these points. When x is 1, function value is 1. When x is 1.5, function value is 1.5. When x is 1.95, function value is 1.95. So when x approaches 2, function value approaches 2. In the second limit, in the second table, I let x approach 2 from the right-hand side by taking these points. Again, function approaches 2. So based on these two tables, I tend to conclude that when x approaches 2, no matter how x approaches 2, from the left or from the right, the function approaches the same number. The number is 2. So 2 is the limit. Example 3. It is one example about a limit that doesn't exist. Consider this function, absolute value of x over x. Here is the graph of the function. At the point x is 0, the function is not defined or not commutable. Plug in 0 in x, then we have 0 over 0. What is 0 over 0? We don't know. So at x is 0, no function value. Therefore, I place two open dots on the graph at x is 0. One open dot means the point doesn't belong to the graph of the function. A solid dot is function value. At x is 0, no function value. So at x is 0, no solid dot corresponding to it. Okay, now in this example, we want to find this limit. We want to find as x approaches 0, what number the function will approach. Again, I use tables to find this limit. In this limit, x approaches 0. There are infinitely many ways that x can approach 0. X can approach 0 from the left side of 0. X can approach 0 from the right side of 0. X can approach 0 by jumping around 0. By convention, no matter how x approaches 0, the function should approach the same number. Otherwise, we say that the limit doesn't exist. I cannot make infinitely many tables to determine the limit. Here, I only make two tables. In the table on the left, I let x approach 0 from the right-hand side by taking these points. The function values at these points are equal to 1 or equal to 1. So this table suggests when x approaches 0 from the right, function approaches 1. In notation, the limit of this function as x approaches 0 from the right is equal to 1. The both calls this limit the right-hand side limit of the function at 0. In the table on the right, I let x approach 0 from the left by taking on these negative numbers. At these numbers, the function values are all equal to -1. For example, when x is -0.5, absolute value of -0.5 over -0.5 is -1. This table suggests when x approaches 0 from the left, function approaches -1. In notation, the limit of this function as x approaches 0 from the left is equal to -1. The both calls this limit the left-hand limit of this function as 0. Now we can conclude that this both sided limit doesn't exist, because when we let x approach 0 from the right, the function approaches 1. When we let x approaches 0 from the left, the function approaches -1. The function approaches two different numbers. So conclusion is, here is the conclusion. So we conclude that the both sided limit doesn't exist. Both sided because x can approach 0 from the left-hand side, can approach 0 from the right-hand side. This limit doesn't exist. But left-hand side limit left-hand side limit exists. It is -1. Right-hand side limit exists. It is +1. The both sided limit doesn't exist.